Greetings, Astronomy 10, and welcome back to part 2 of your lecture series for chapter 15. And today we're going to wrap up our exploration of the Milky Way. Last time we left off talking a little bit about what the Milky Way is made of. Obviously, it's made up partly of luminous matter, stars, and things like that. It's also made up partly of gas and dust, but mostly it's made up probably somewhere between 90 and 95% of stuff that we can't see, things that don't emit light. We call that dark matter. And we don't know what that is, and so we called this whole situation the dark matter problem. Now let us remind ourselves of a few things. Uh, How do we know that the dark matter is there? Well, we have this rotation curve, right? Excuse me. That shows essentially that if there was just the matter in the disk and, the globular clusters, the things that we could see, essentially stars that are further away from the galactic center, things that are further away from the central bulge, from the galactic core, should move slower, right? Like planets orbiting the sun farther away move slower than planets that are orbiting more closely, right? It's just gravity, very simple. However, we know that there's a tremendous amount of dark matter in a spherical halo around and in, of course, galaxies like our own, because stars pretty much all the way out to the end of the disk that makes up the Milky Way are kind of moving at the same velocity. Obviously, that still means that stars that are further out are going to take a longer time to make their loop all the way around the Milky Way, right? Because they have a much greater distance to go than stars that are closer to the galactic core. But they all still move at about the same speed, and the only reason, and the only way that that's possible, the only reason that that could happen is if there's a ton of other matter pulling it around, causing a gravitational influence on all of the stars that are in the disk of the Milky Way for them to move that quickly, right? So we can see how the material in the disk is moving, and therefore we know how much mass is driving it, right? Causing it to undergo this gravitational acceleration, right? Have this gravitational force and make it move. If we look at, you remember last time we talked about the forbidden band, if we look at the 21 centimeter radiation from the disk, we can see that half of it is moving toward us and half of it is moving away from us, meaning that the Milky Way has to be rotating, right? If half of it is moving towards us and half is moving away, it means it's rotating, right? And so we're sure that the Milky Way, the disk at least, is sort of revolving about the galactic center, right? It's rotating. Everything outside the disk, of course, things like globular clusters, are kind of moving, in random directions. And so it's a little more difficult to get a sense of exactly what they're doing, where they're going. However, we can still measure their velocities, the radial portion of their velocities, from the red or blue shift. And so we've been able to plot out that most of the objects that are outside of the disk of the Milky Way are orbiting around the central galactic bulge, right? The core at the center of the galaxy. Now, if we want to try to use Kepler's law, Kepler's third law, and if you remember, that's the relationship between the square of the period and the cube of the semi-major axis of the orbit of a planet around the sun. But the same should work with any mass around any other gravity well, right? And the important caveat there is that we have to use the astrophysics version that has the sum of the masses, that n squared a cubed equals mu, right? Where mu is m1 plus m2, the sum of the two masses in the gravitationally interactive system. And so we want to try to use Kepler's law to find the mass of everything, all of the luminous matter, in between the galactic core and the sun. And if we do that, we have to look at how far we are from the galactic core. And if you remember, that's something like 27,000 light years, right? We're about halfway or so in between the core and the edge, the rim, what they call it, the edge of the disk of the galaxy. That's about 1.7 billion astronomical units, pretty far. And the time that it's supposed to take us to go all the way around is something like 23 million Earth years. Crazy, right? Now, if the sun is one solar mass, that means that the galaxy, with that distance in time, should have about 93 billion solar masses interior from our orbit to the center, right? That's, the inner half of the radius of the disk. If we look at the rotation curve of other objects, things that are further away, we can see that objects far from the core still have really high velocity, right? All the way out to, if we look at, say, the Large Magellanic Cloud, which is one of the dwarf galaxies that we're currently cannibalizing, we of course being the Milky Way, that's about 160,000 light years from the galactic core. And even out there, objects are moving, very fast, the same kind of velocity. Thus, the mass of the Milky Way is probably closer to 1.3 trillion solar masses. It's a lot. And so that's probably a little more accurate. We believe that at the core of our galaxy, in the middle of the central bulge, is an object called Sagittarius A star. Now, before everyone gets confused, we usually write that as a capital S, lowercase gr, and the next word is a capital A with an asterisk, Sagittarius A, and then you pronounce the asterisk as star, Sagittarius A star, because it's a star. In any case, it's, we think at least, at the exact geometric center of the bulge in the center of the Milky Way, at the core of the galaxy. And then when we look at it at various bands of the electromagnetic spectrum, we can see that it's bright in several portions, not the least of which are X-ray and radio and also infrared. We can see that there's a bunch of superheated gas there, a very, very hot gas. And in order for gas to be really hot out in kind of the vacuum of space, there has to be some sort of impetus, some reason for the gas to be that hot. And we think that one of the possible explanations for all of that localized heat to be out there in the center of the galaxy is possibly that there were a bunch of supernova events that heated up a bunch of the gas and kind of dispersed a bunch of the energy into the gas in that region of space where, the gas is a little more dense because of obviously gravitational interactions and so on. When we look at it in the infrared, we can see there are actually hundreds of thousands of stars, tons and tons of them, in the core of the galaxy. And so that means probably there's a lot of gravitational interactions happening there in the core of the galaxy, right? If you have that many stars in a smaller volume, obviously they're going to, pull on each other, right? That's what gravity does. It's an attractive force, right? It pulls things towards each other. If we look at the same region of space in the radio portion of the electromagnetic spectrum, there's actually an image of it. It's It's the 11th, I think, image in today's image bank. Yeah, I think that's right. It's the one with the purple and orange features in it. The purple is there, probably from synchrotron radiation, if you remember. Probably that means that there are very strong magnetic fields in that region. Obviously, you have that much matter moving around, it's going to make a very strong magnetic field. And so we think that there's tons of synchrotron radiation, possibly from cosmic rays, if you remember from last time. The orange regions are most likely, a little bit cooler, right? Those are what we would call nebulae or molecular clouds, right? And when there are molecular clouds, of course, there is the potential for star formation. Possible, right? Although it's unlikely that if there's tons and tons of gravitational interactions that it's going to be able to settle long enough. So, also something to think about. In any case, if we follow the orbits of stars that are near the central bulge, and there's a nice diagram of it. That's I want to say the 14th image in today's image bank. There are a bunch of elliptical orbits that all kind of that orbit around the central bulge. You can kind of see that the one common space is this part, like in the middle of the image. And all of these stars are orbiting this object, Sagittarius A star. And if we follow these orbits, we realize that there has to be something really, really massive there, something more massive than a star, right? Probably a hypermassive black hole. We estimate that the hypermassive black hole, this object, Sagittarius A star, could have a mass of up to 4 million solar masses. Now, believe it or not, as galaxy nuclei go, as the hypermassive black holes at the cores of galaxies go, because basically every galaxy that we've looked at has a hypermassive black hole at its core. As these go, 4 million solar masses is actually kind of on the small side. The typical number that we see is usually something closer to like 100 million solar masses. And the only thing that can be that massive, of course, is a black hole. Right? Black holes can actually get more and more massive by combining. Typically, when black holes combine, they let out a huge gravity wave, and that was one of the events that we detected at LIGO, at the Laser Interferometry Gravitational Observatory, and that sort of proved the existence of gravity waves the way that Einstein thought. That was just a few years ago. Anyway, that's kind of on the small side for galaxy nuclei. Typically, they're much, much larger. Some of the superheated gas at the galaxy core is coming from a bunch of different sources, like 9,000 or so X-ray sources. And what this means is that likely matter is falling into the core of the galaxy, into this hypermassive black hole. Now, we're not 110% sure of the meaning of the gamma ray telescope's findings, but we speculate that it could be because there were bubbles, if you will, that formed after a massive burst of star formation, some millions of years ago. Or they could be from material falling into the supermassive black hole, which would make the event much more recent, maybe 20,000 years ago or so, possibly repeating since then. Either way, what that seems to point to is that in all likelihood, even these high energy objects, right, all of these things that are sending out gamma ray bursts, are also moving toward the black hole, right? So long story short, you have an object that's that massive, 4 million solar masses. Not only is it able to basically pull tons of stuff around it, like, an entire galaxy, even though the dark matter is really what's kind of responsible for making it move at the velocity that it's moving at. But when you have an object that's that massive, it's going to make stuff pull towards it, right? And eventually things are going to fall into it. No surprise, right? Now, one of the important things that we learned from trying to study the Milky Way is that galaxies generally do not exist by themselves. We say in isolation. Most galaxies exist in groups. And ours is no different, of course. The Milky Way is part of a cluster of galaxies we call the local group. And we talked about that as far back as the beginning of the semester. And there are something like maybe 50 or so members of this local group. Now, what makes the local group special and significant is that all of these galaxies in the local group are gravitationally interacting. And eventually, at some time, way, way down the road in the future, theoretically, they should all kind of become one large galaxy, one really hypermassive galaxy. Possible, right? Stands to reason. Most of the galaxies are not large like the Milky Way. As a matter of fact, the Milky Way and the Andromeda Galaxy are the two largest members of the local group. Both of these galaxies, us, the Milky Way, and the Andromeda Galaxy are both barred spiral galaxies. The only one that even comes close is a galaxy called Triangulum. It's named Triangulum because it's kind of off in the direction of the constellation Triangulum, which is actually just 3 stars that make a triangle, as you might have guessed by the name. But it's not a barred spiral like the Milky Way or the Andromeda Galaxy are. The Triangulum Galaxy has maybe a tenth of the mass of the Milky Way, whereas the mass of the Andromeda Galaxy is much closer to ours. The other 30 or so galaxies that make up the local group, or maybe even, 40, close to 50, because there's about 50 members in total. But most of them are what we call dwarf galaxies. You remember there's dwarf galaxies and there's giant galaxies, right? Most of them are dwarf galaxies, small galaxies. At least a few dozen of them. In any case, however many there are, this 50 or so galaxies are special and significant to us because they're all gravitationally interacting, right? And eventually they're all going to become just one mega giant galaxy. We think that the Milky Way probably formed when a large chunk or cloud of dark matter collapsed into small proto-galaxies, some of which are still around and probably orbiting around the Milky Way. The large and small Magellanic Clouds are probably the largest of these. The Sagittarius Dwarf Galaxy is kind of making its way through the disk of the Milky Way now, and as it does, the tidal forces of the Milky Way on the Sagittarius Dwarf Galaxy are tearing it apart, right? They're disrupting it. And as a result, we're stealing bits and pieces of it, its stars. Essentially, we say we're cannibalizing the galaxy, right? Just like we are going to do with the Large and Small Magellanic Clouds, and indeed all of the galaxies in the local group. Eventually, we're all going to merge. Long story short, proto-galaxies, or tiny little galaxies that formed in pockets of dark matter, merged to form the Milky Way. Stars formed in several places, obviously in the bulge in the center, and that may or may not be happening at the same rate as other places in the Milky Way, namely the disk, of course. But stars also formed in the halo, if you remember the globular cluster structures, right? There were stars that formed out there in the halo. Mostly those are much older though, something like 13 billion years old, right? These globular clusters. And also in the disk of the Milky Way, where there is still tons and tons of star formation going on, which is why the spiral arm structures that make up the disk of the Milky Way still have that brilliant bright blue color, because class O stars and class B stars, while there are fewer of them, they are so much brighter than any other stars. Right? They're so much higher up on the HR diagram that they shine so much brighter, and they kind of outshine all of the red stars and orange stars and yellow stars and so on, right? So the first stars formed in the halo, some of them in globular clusters. Gas in the disk formed several generations of stars. Obviously the big bright blue ones, or the really hot ones, don't live as long, right? And while fortunately there's still star formation going on to give the spiral arm structures that bright blue color, there have obviously been several generations of these if there's still star formation going on, right? You're talking about 13.7 billion years of stellar processing potentially. And there's a concentration of mass, mostly because of gravity, of course, near the core, this central structure at the center of our galaxy. As we'll see soon, that's not uncommon for especially spiral arm galaxies and barred spiral galaxies to have these hypermassive black holes and central bulges at the core, at the center of the mass distribution of these galaxies, right? And also, it would be odd, strange for us to think that other galaxies also didn't have dark matter halos that they existed in. And that also means that, especially for other barred spiral galaxies and other spiral arm galaxies, that they shouldn't have similar disk structures, that they shouldn't have, if they're going to have bulges and halos, right, that they shouldn't also have similar disk structures to our own. The one thing that is really weird about our galaxy in particular, compared to most of the other spiral and barred spiral galaxies that we've seen that are about our size, is that our hypermassive black hole at the center really isn't that hypermassive compared to a bunch of the other ones that we've seen. And so we're kind of a peculiarity, but not a massive peculiarity. There are a few that have sort of lower mass galactic bulges, but not that many. We're kind of an outlier, but not a terrible outlier. In any case, that's basically all that we have for today. If you have any questions, I know we kind of got into a bunch of nitty-gritty today. So if you have questions, of course, you can get a hold of me through the usual channels, like normal. But that basically wraps it up for the Milky Way and how we think galaxies essentially form. In any case, I hope you enjoyed today's lecture as much as I have enjoyed giving it, and we'll see you next time.